All right, we're going to run through Ethereum storage proofs today and some of the work we've been doing to make them work in a zero-knowledge SNARK and in the browser. I'm Jeff, one of the co-founders of Aztec, and we've got Sean here as well, if you want to give a quick intro.
Hey, yeah, I'm Sean, sometimes go by Malia. Yeah, I'm a protocol engineer at Aztec.
Awesome. So yeah, today we're going to run through kind of in detail what a storage proof is, kind of how they work, and how data is stored on Ethereum. If that's kind of that doesn't hit the nail on the head, we'll do some learning by examples, which can help. In more detail on how storage proofs actually work on Ethereum, and the underlying data structures kind of used. And maybe then some text on kind of why we would want to do this in a ZK-SNARK, some of the benefits compared to normal storage proofs, and if we have time, a quick demo on kind of this end-to-end working and kind of the missing pieces to get this working in a browser. Cool. So what is a storage proof? So my take on I guess trying to sum this up in a sentence is a verifiable claim that something happened on Ethereum. So that something could be a payment, a transaction, just a piece of state exists in the Ethereum state tree. And the key part here is that it's verifiable. So you can prove that happened to someone else without having to give them the entire Ethereum kind of database. Still not that clear, so maybe we can look at some examples to make things a bit clearer. So I guess the most commonly used one is proof of payment. So let's say I want to pay Sean 1 ETH, and I want to kind of prove that I've done that to a third party or smart contract. I can use a storage proof to actually prove a transaction happened on Ethereum and prove that the balance was 1 ETH and it went from my address to Sean's address. Another popular example is kind of the CryptoPunk example. So you can prove that you own a particular NFT by proving a value in a contract's storage root. We have a demo of this later on to prove who owns the first CryptoPunk. You can also do this for kind of any NFT, and this can be used to do kind of gated voting or similar kind of actions. And the most interesting one, which would have been useful around the FTX time, was kind of proving that a kind of centralized exchange's balance is above all its like liabilities. So you can do proof of solvency with storage proofs. You can sum up multiple different accounts and kind of prove that the sum of the assets is greater than the liabilities. Cool. So maybe over to Sean to go through how these actually work in detail. Sean, you're on mute.
Whoopsies. So this here is an example of what is inside an Ethereum block. So at the top of the block, we have basically a lot of metadata that makes up the block. And then the main ones that we are interested in are these things called the state roots of a series of tries. So each try so the world state try represents the state of all contracts. And then if you go further down to the account state, you can then prove particular storage slots inside a contract. So we pop onto the next slide. For the example of proving a piece of storage in an Ethereum smart contract, these are the tries that we care about. So with the account storage try, I can prove a particular storage slot. So for the CryptoPunk example, I will look for a user's address in the balances mapping, and then from there that will be stored in a particular path in this accounts try. I can prove all my way up to the top to the storage root, and then I can go into my world state try, prove all the way up to my world state, and then I'm in the block hash. in the block. And then if I can recalculate the block hash, I can prove that this piece of state does exist. So to go over like what these proofs actually look like, we can start with something quite simple. So we have like a Merkle tree proof. So to do a Merkle tree proof, I take the node that I want to prove about, and then we'll have to click a few times here to work our way up the tree. So I get the sibling path and kind of hash my way up till I get to the root. And that is how if I can recalculate the root of the tree, then I can, with 100% confidence, or pretty close to it, confirm that the value that I was proving exists within the tree. So this gets a little bit more complicated with Patricia tries. So instead of it just being a binary tree where we hash one piece of data, well, two pieces of data all the way up, we instead have a choice of things to hash. So this is why these become very expensive within SNARKs. So for example, if I take a particular storage slot, let's say it's storage slot 0 within a contract, I hash it to get the path in the root of the data trie, and then I follow that path to get to where the leaf, the data will be stored. And this path can be made up of either a branch node, which is kind of like a traffic junction that splits all 16 potential hex values of each nibble in the path. And then it can have these extension nodes, which are kind of shortcuts, and then leaf nodes, which store the values themselves. So each proof is made up of a combination of these. So this is what a branch node looks like. So let's say that I am going from, the hash is 0A, and that's the path that I'm going to go down. I would first go to the node on the very left, this hash on the left, and then that will be stored there, will be the subtree, the hash of the subtree underneath it. And to get the hash of this entire node, I hash everything together. And then there's also extension nodes, which basically contain what we call shared nibbles. So let's say that I only have one piece of data in an account, and it's one value. It's a bit wasteful for me to have 32 branch nodes to get to the very bottom of the tree. Instead, we have this thing called these extension nodes that basically fill in the gaps. So if I can basically store 30 nibbles here and then only have a tree that's of depth 3. So it allows us to have shallow trees. And then at the leaf, we will have, again, just the hash of the key itself. So the path that's been taken to get to this leaf, and then the value itself. So what is the key? As I said earlier, the key is going to be the Ketchak hash of the storage swap. And then the tree is traversed with a combination of the 3 nodes that were shown above. And this is a little small example that kind of demonstrates what the branch node, extension node, and leaf node are actually doing. So if the path for a particular hash is 1, 2, 3, 4, 5, 6, I will have a branch node at the top. And then as the first nibble of my path is 1, I can then take the 1 in the branch node. And then instead of having 5 more branch nodes, I can just have an extension node that takes me straight to my leaf. And this is a depth 3 tree. I'll try. And what does the proof of this look like? So as the depth of the tree is only 3, I only have 3 values in my proof. And the proof is going to be the RLP encoding of the hash of each particular, of the data in each node. So for the leaf node, it will be the RLP encoding of the key with the value itself. And then on the extension node, it's going to be the RLP encoding of the extension with the hash of the child's tree. And then the branch node is going to be an encoding of 17 hashes, or 17 32 bytes, because we have a sub hash for each of the subtrees, for each of the potential branches. So it's a huge piece of data. And what makes these very expensive in SNARKs is that we have to pay for the branch node at every leaf, at every level of the tree, which is suboptimal. So to get a storage proof, I can simply ask an Ethereum node for one. They all have this very handy method from EIP 1186 that allows you to define a particular contract and storage slot that you would like to get a proof for, and it will give you a storage proof all the way up to the block hash. So this is an example of a storage proof for the owner of CryptoPunk with ID 1. So, and this is particularly the proof within the contracts data tree. So this is a 5 deep Patricia trie. As you can see, there are 3 large blobs of data. They are the 3 branch nodes in our proof. And then we have 1 extension node, which is the second last piece of data. And then the last piece of data is the RLP encoding of the actual leaf itself. So to zoom in on what the first branch node step looks like, this is the RLP encoding of it. And then in the next slide, this is what it is when it's decoded. So we can see that there are 16 hashes, 1 for each hex numeral. And then we have an empty value field, which also exists on the branch node. So this is just, the big blobs aren't too scary. Once you RLP decode them, they're simply just representing leaves of the tree. This is the leaf node at the very end. So as we can see that when you RLP decode it, we have the key, which is the hash of the storage slot itself. And then we have the piece of data. So for CryptoPunk 1, the current owner is the address 0x94. And yeah, that is a storage proof and how they work.
Cool. So I guess if these Ethereum nodes have built-in methods to get the data needed to kind of attest to this claim that something exists on Ethereum, why do we need to make this more complicated and do it inside a zero-knowledge proof, or why do we need to write this in a Noir circuit? And I guess like to look at that, we can kind of look at these examples again on the next couple of slides. But I think normal storage proof, the way I think about this is it convinces a verifier that the state is correct. So you can use this in a light client to kind of prove that the current state of the Ethereum blockchain and kind of make some action based on that. You could use it in a smart contract where all the data is kind of public, but you don't want to pay a heavy cost for read items in Solidity. So you do a lot of read requests in storage proof. There's some interesting research on Uniswap TWAP oracles that use this mentality. You can prove the price of like ETH and DAI is between a certain range for the last 100 blocks to get a very accurate representation of the price. And really, it's kind of normal storage proofs are done when you need kind of efficiency over the data, or one of the parties involved doesn't have all of the data available. So you need this kind of efficient proof representation using a Merkle path. The main downside, though, is everything is public. So in all of these examples, you can see kind of all of the parts of the tree that you're hashing, and most importantly, you can see the leaf node at the end. So in our CryptoPunk example, Sean was able to kind of query an ETH node and figure out which CryptoPunk we were talking about, what the ID was, and who owns it, so which address. And that's kind of where normal storage proofs fall down, and the start of why we want to do things inside a zero-knowledge proof. So to try and kind of put some color around this, I've updated the definition to kind of describe what a zero-knowledge storage proof may be. So here, I think it's kind of letting you prove something happened on Ethereum, but without revealing what to the world. And that may sound a bit abstract, but kind of the last part of disclosing what is what the ZKP adds. So we can look at some examples. We'll go through the examples earlier on in the slides and kind of add zero knowledge on top of them to see how the example changes. So for the payment, we can now prove that Bob paid Sally without revealing to the world that it was Bob doing the payment, or that Sally revealed the payment, or even the amount. So depending on the application, you may want to kind of prove you bought a ticket without revealing your identity. Those sorts of applications now become possible. Again, in the CryptoPunk example, I can prove that I'm part of a kind of NFT community without revealing who I am or which NFT I have. So a lot of this came out of some of the NounsDAO work, which we'll talk about in a minute. But kind of this enables private voting semantics, not kind of revealing who you are when you're voting. And the last one, kind of for an FTX style proof of solvency, most exchanges don't want to kind of reveal the sum of their assets or their liabilities. It's kind of business secrets. So wrapping this in a zero-knowledge SNARK can kind of obscure what your wallets are, what the kind of total size of your balance sheet is, but still give a guarantee that the liabilities and assets add to zero. So some kind of rationale to try and see why we want to do this in a SNARK. And as I was saying on the previous slide, a lot of this research that we're going to kind of look at on the next slides came from a kind of 3-month research sprint with Aragon, which was undertaken as part of a NounsDAO RFP. The goal for the sprint was to kind of take a storage proof and use it to enable private voting in the browser. And so, like the CryptoPunk example, in this case, we wanted to prove that a user owned one of the NounsDAO NFTs and enable them to vote privately on treasury proposals for the Nouns community. And over the last 3 months, we've had to do a lot of work between ourselves and Aragon to make this possible. We'll go through some of these now, but it's not been an easy road, but we've made a lot of progress to realize this vision. I think the initial circuit size for a storage proof didn't really even compile. So it was around 40 million constraints, and really you can't prove that on any AWS machine, let alone in the browser. So we had to do some pretty serious kind of engineering and upgrades to start to make this more feasible. The main one we did to kind of lower the constraint count was upgrade the backend proving system that Noir uses. So we moved from TurboPlonk, which was something we made in 2021, to the much faster UltraPLONK, and that kind of reduced things by probably 5x in terms of constraint count. We also had a lot of refactoring in the Noir compiler to kind of have a lot less bugs, but also have things like dynamic array indexes. And we also have a very efficient Keccak custom gate in UltraPLONK, which the majority of the constraint reduction came from. I think we reduced the cost of a Keccak kind of hash from around 160, 180,000 constraints to around 18,000, which is a huge win, especially given the amount of Keccak hashes needed in the Merkle-Patricia trie hashing. So yeah, just a summary of those optimizations here. And the last point is kind of one that actually kind of brings this into production. So in order to get this working in the browser, we've had to do some work to work around the limits of what's possible. And to do that, we needed to have recursive proofs available in the browser. So now with UltraPLONK, we can do, as I said before, very efficient Keccak hashes, dynamic array indexes in Noir circuits. So you can have much more fancy for loops for RLP encoding, and these recursive proofs to bring it all together. So trying to put this into a SNARK still is not the fastest. So we can look at kind of the raw amount of compute needed here. There are roughly 5 Keccak hashes per level of the tree for the simple NounsDAO circuit. I think it can be up to around 16 in the worst case scenario if all of the branch nodes are full. But for the NounsDAO contract, it's not that large a tree because there's not many nouns holders at the moment, so it's a bit smaller. Lots of RLP encoding. Every hash is RLP encoded before it's hashed. and there's lots of hashes, so that's a kind of a large cost. And yeah, depending on the activity in the contract, the tree can be anywhere between 8 to 32 levels. For NounsDAO, it's around 5 to 8, and for the CryptoPunk example, I think it's less than 5, which we'll see in a second. So even with this, we're still seeing circuits of around 800,000 constraints, and this is kind of an issue because the WASM limit in the browser is around 512,000 constraints, just based on how much memory the proving or the prover will use in the browser. So we had to make some kind of adjustments here, and the end version of this will rely on the recursive proof construction we talked about previously to actually get this working. So what is recursion? Recursion lets us verify a proof inside a proof. So instead of having to make a very large program and kind of prove it all at once, we can chunk up the program into smaller pieces and layer them together to create arbitrary complex proofs. So we still have to do the same amount of proving, but we can kind of split them into chunks and break down a larger program into something that can be proven in the background on a user's device. And the key thing here is that we can prove it in the browser now. So we can break the complex storage proof down into 512,000 constraint chunks and verify those in the browser inside one single recursive proof. And for like Ethereum, this means we only have to pay one gas cost to verify one proof. So we don't have to kind of verify each proof individually on Ethereum, which will get very expensive. We only have to pay for one verification. And a rough schematic of how this could look. In this case, if we have a small kind of Merkle-Patricia trie, we can just do 2 proofs, one which proves the first 4 levels and one which proves the next 4 levels, and we can kind of recursively verify those together in one zero-knowledge circuit. And so depending on the size of the tree, you may need more levels of recursive aggregation, but for simple storage proofs, you can get away with 2 like this. We'll update this slide to actually have the relevant links to packages, but most of this work now is on GitHub or NPM. There's a storage proof library written by the awesome folks at Aragon, which can be used on the command line and is being updated to work with the recursive construction in the browser. You can also generate recursive witnesses for proofs in the browser. That's now working. And proving in the browser works with Next.js, and you can prove kind of up to 512,000 constraints. There's an NPM package for that. And we have examples of recursion working in the browser, which is being worked on as well. Do we have time to do a demo, Sean?
Yeah, can do.
Cool.
All right, so I'll show my screen. I'm just going to share my terminal. Hope you guys can see this. So this is first of all a TypeScript script, which is going to basically use Alchemy's API to get the proof. I'm using Alchemy's API because they bundle everything together. It's quite nice. They also give you the current storage hash as well, that the default doesn't give you. You have to make an extra API call. But yeah, so I get, this is the address of the CryptoPunks, and then this is the storage slot where the first owner is basically stored. So then I'm writing all of these into a Nargo prover.toml, and that I will then prove. So if I just run that script here, so that will write the proof to our prover.toml. And if I go into what we're looking for here. So it's going to be this is our Noir code that basically uses the library that Aragon have created, which is the storage proof library, and takes in the proof from our prover.toml, and then basically constrains that the storage proof is valid for this storage route that we've just requested from an Ethereum node. So if I go into this terminal right here, I can run an Argo proof demo, and it will build the circuit and then construct a proof. And then I can verify that same proof really quickly. So this takes around 20 seconds because it's constructing the proving key of the circuit as well, which takes up most of the time. And then, so that's verified. Well, that's worked because there's no output. So I can then run verify, and this is now reconstructing the circuit to reconstruct the verification key, and then it will verify the proof. And this will take, to do everything, 18 seconds, but the actual verify step is milliseconds. So yeah, that's just run successfully. I can also just hop into the prover.toml as well, so you can see what that looks like. Oh, whoops, wrong file. Oh, it's just going to be in here, isn't it? Prover.toml. So this has the proof itself, and then it's quite a large proof. It's just an array of bytes, and then the value that we're proving. So this is the Ethereum address, and then we have the storage route that we're calculating against. And if I run this script, this will regenerate these values, which is handy.
How many gates is this? It's under the 512,000, right? It's
yes. So this is, I think, yeah, 434,000.
Yeah, so you'll be able to take this directly and use this in the browser without recursion. But if you cross over the 512,000 kind of limit for kind of more popular contracts, or need to do more things in your circuit, on the left-hand side here, we've only got kind of a simple assertion that the storage proof is valid. We're not doing any EasyDSA or any other logic really. So depending on how complex the program is, you may need to split this out into two proofs and recursively verify them, or you may get under the limit to be in the browser.
Yeah.
Awesome. I think that's everything. So we'll link the kind of links in the description of this when it gets posted, and please join our Discord if you want to hack around with this, and someone will be available to help you.